So in this video, we're going to continue our discussion on computational thinking, and we're going to kind of wrap that whole framework of thinking up with the concept of modeling. And I'm going to go through some slides here, and then later in the video, I will actually switch over to a modeling software and kind of show you some examples of what models can do for us in programming. So let's talk about modeling, though, just some concepts of modeling and how it's useful, different types of models that we can use, so on and so forth. So like it says here, modeling is a fundamental practice of computational thinking. We use modeling a lot, even if we don't really realize that we're using it. It is a form of abstraction. So if you remember abstraction from the last video, we said abstraction was at a very high level, a lot of details are kind of obscured from the person who's looking at that abstraction. And at a very low level of abstraction, not many details are obscured. So high level is more vague, low level is more specific. Abstractions can take many forms. Some examples of that, if we think about a calendar, right? A calendar is just an abstraction of time, right? Time being a very complicated construct. If we use a calendar, we can kind of model that or abstract time to a form that we can kind of understand, right? We have days, we have months, we have years. That's an abstraction that we understand. A loop and a subroutine is also an abstraction. So if we remember loops or iterations, we said we can use loops or iterations to execute the same series of steps over and over and over again without having to write those steps out a ton of times. So we're kind of abstracting the idea of this is going to be executed several times. I'm just going to write it once, and that could be a form of an abstraction. A subroutine, basically just a set of steps that you may want to call upon at a given time, is also an abstraction. Continuing on, modeling is useful to us because it helps us improve our understanding by only focusing on the relevant parts of a problem. So again, modeling shares a lot of common traits with abstraction because it is like a subset of abstraction, right? So we said abstraction also can help us improve our understanding of something by only really focusing on the parts that we need. And remember, we said that context was key in that because the context of the use of the abstraction really kind of determines what you're going to obscure and what you want to be shown. So if you remember that metro map, we're only really wanting to use that map in order to navigate a metro system, so to see where the stations are, which station comes first, which one's last, or if there are any crossover kind of things. That's the context there, so that abstraction is only going to show that information. But back to modeling. Modeling really only shows entities of the solution and their relationships. And just some vocabulary here, when I say entity, that's just a core concept of the system, and a relationship is just connections between those entities. So if we think back to the metro system, right, each of my stops might be an entity. That's a core concept of the system. The relationships might be any kind of connection that relates those entities together. So any specific lines that link those entities together, maybe any other like specific things we might want to know. So we can understand models because we have something called an imagination, hopefully. All models hide details of the reality that they represent, right? And there's kind of a little chart here. So a part of reality is represented by a model, which kind of hides some details of that part of reality, right? So many models exist. There is not just one kind of model. They're all over the place. The variety of the relationships are endless, right? A couple of examples here, though. Maybe we have A, something called A, that belongs to B. Maybe C contains D. E happens before F, right? We don't know what A, B, C, D, E, or F even are. We don't know if they're numbers. We don't know what they are. But we can wrap our heads around okay, B belongs to A somehow, D is contained inside C somehow, and E must happen before F, right? That's a very basic model, but we can understand what that's saying even though we don't know what these letters represent. And these relationships are directional, right? A belongs to B does not mean that B belongs to A, right? These are directional. C contains D does not mean that D contains C. So our model relationships are directional. Another example, B owns A, D is contained by C, and F happens before E, right? There's another example here. So this is a differently worded one. Some of these are different, right? Here, F happens before E. But here we're saying, okay, well, B owns A, instead of saying A belongs to B. Instead of saying C contains D, we're saying D is contained by C. All right, so the relationships on these first two are the exact same. They're just modeled or written in a different way. So let's talk a little bit more about entities and relationships. So when I'm talking about an entity has kind of a couple of things that we want to keep in mind. Entities have properties, and all a property really is just a piece of information about that entity. So something like a name, right? Let's say that my entity is called person, right? I'm modeling a person. Person has all kinds of properties, but one of those properties might be the person's name, right? It's just a piece of information about that entity. Type is the classification that the entity belongs to. So, for example, our metro map from last week had styled lines, which created a type that connected entities. So if we go back here, I'm going to actually go back to that metro example. We can kind of see what type we're dealing with here. Here are my entities, maybe, right? My metro stations. These lines are the relationships that connect those stations together. And let me go back to the slide. Okay. So we've talked about properties, we've talked about type. Some rules, so entities also can have rules, and a rule is just a statement about an entity that must hold true. For example, the metro map has a closer for a set number of days. That is a rule about my entity. Behavior is a description of action in natural language or algorithmic form. So, for example, the metro has a line that requires trains to travel slower. All right, so I went back to my metro map here. You'll see we have a key that has different styles of lines on them. And these different styles of lines, going back to the type, right? These different styles of lines kind of determine which type of relationship is happening between my entities. But some of these lines may mean something else, right? This line here may mean that the train needs to travel slower. Maybe the train can't travel as quickly if there are curves, like this line here. Again, context is important there. All right, so that's rules and behavior. Now let's talk about the two kind of main types of models that we have. We have static models, which give us a snapshot view of the system at a single point in time. So static model is just kind of like taking a picture of something, right? It only shows you the system at that point in time. A good example of that would be that metro map, right? The metro map may need to be updated. Let's say that they add a new track, maybe one of the stations is closed, maybe one of the tracks is closed down for maintenance. Your static model would then need to be updated, right? You'd need to take another snapshot of that system that reflected those updates. On the other side of that is a dynamic model, And the goal of a dynamic model is to explain changes in states as time passes, which involves a couple of things here, right? So what is a state? A state is just a description of my entities at a specific point in time. When I say transition, that is a change in state. An event is something that triggers a transition or a change in state. And then an action is some kind of computation that is carried out as part of this transition. So dynamic models kind of involve all of these things here. For example, we have a turnstile, right? So a turnstile is that thing that you got to push through and it always hits you in the hip and it hurts really bad. A turnstile, right? A turnstile is a good example of a dynamic model. We can model that very dynamically, right? And I'm going to kind of walk through this model here. It looks a little confusing, but it'll make more sense, hopefully, once I explain it. So let's start at the beginning, right? At the start point, which is this black dot. So we have different kinds of models, right? I'm going to take a little aside here. We don't really go into state machine diagrams in this course. That's more of a software engineering concept. But a state machine diagram is an example of a type of model, right? And it basically just shows states of entities at given points in time. So our start point in a state machine diagram is the black dot. That tells us where we are at the beginning of our order of events. Okay, so at the start point, the turnstile is in a locked state, right? So my states are shown here. I have two states, locked and open. So my turnstile is in a locked state. Let's think about an event, right? If I insert a coin, that's an event. That would trigger a transition from the locked state to the unlocked state, or the open state, right? Pushing the unlocked turnstile triggers the transition from an unlocked state back to a locked state, right? If I push a locked turnstile, like we see over here, nothing will happen, right? If I don't put a coin in to push my way through the turnstile and I just start pushing on it, it's not going to unlock, it's going to stay locked. So we're kind of in a loop here if you just push on the locked turnstile gate. When I insert a coin, my state changes, right? And remember, a change in state is what we call a transition. So if I insert a coin, I transition from being locked to open or unlocked. If I keep inserting coins into an unlocked gate, it's going to remain unlocked, right? When I push the unlocked gate and go through it, it's going to lock behind me. So the next person has to put a coin in if they want to pass through, right? So that's kind of an example of a dynamic model that deals with changes of state, transitions, actions, all that. Like I said, we don't really go too far into this in this class, but it is good to kind of know that it exists. We're mainly going to be focusing on static models of our programming entities in this course. So a good example, a real-life example of using a model. There's a man named Leonard Euler who was challenged to determine whether it was possible or not to walk across all 7 bridges in his town only one time. And at the time, the map of the town was very cluttered and had a lot of distracting detail, so he made a model of the town. Specifically, he made a graph that uses nodes and edges. And you'll hear the term nodes and edges a whole lot in computing, not just in this class, but in networking. You'll hear it in database. You'll hear it in data structures. It's a very common thing that we use. So a node represents an entity, and the edges represent my relationships between those entities. So here's an example. Here was the map of the town that he was in, and if he's trying to determine if he can walk across the bridges of this town, this map is not the most helpful, right? So what he did was he took this map and he turned it into a very simple model, My nodes, or my entities, are the different kind of landmarks that the bridges link together. So the North Bank, the West Island, the South Bank, and the East Island are all connected by bridges. My edges here, or my relationships, represent those bridges, right? So there's 2 bridges between the North Bank and the West Island. The West and East Islands are connected by 1 bridge, so on and so forth. So that's just a pretty simple example of what a model is, right? And again, I'm gonna bring back abstraction here. This is a very detailed, very specific map. This is a very vague map, but the context of just seeing what was connected by bridges, we can abstract all of this detail out with the exception of the bridges themselves and the names of what they connect, right? A dynamic model. How do we execute a dynamic model, right? Thinking about that turnstile example here. Once we adequately define a dynamic model, they can be executed. So an example of that is an orrery, and I'm not going to say that again because it's really hard to say, which is a planetary dynamic model that accurately shows the position of planets. And you may have seen these before. It's like a clockwork planetarium kind of thing, right? So in the middle we have the sun, and then we have the position of the planets around the sun at a given time reflected accurately, right? Now these models typically require a parameter to show where they need to start. So you couldn't just build this thing and turn it on and it would immediately show the accurate position of the planets, right? We need like a starting parameter. Say the planets are here at this point in time. Now we can turn this thing on and they will remain accurate, right? So that's an example of a dynamic model. We also use models to demonstrate data and relationships of data. So let's think about how we would do that. So a solution, right? Any kind of solution to a problem is probably going to use some kind of data, right? If we think back to that palindrome lab that we did, we didn't have a whole lot of data there, but we did have some, right? We had the actual phrase or word that we wanted to see if it was or was not a palindrome, right? Now that was a pretty simple algorithm. Obviously, some solutions we could have would be a lot more complex, right? So let's say that a university wants to design a solution that's for storing student records. So we want to store student records in some kind of program, right? So my entity here would be the student. And the student, we could say, I'm going to model this data out. The student has a name, an address, a phone number, and a date of birth. So these belong to the student. And we're reflecting that in this model here. Now, that model we just looked at is pretty limited, right? We could distinguish between students who are local and those who are out of town. Some students could have more than one phone number. And we could add something called a cardinality that would fix that, that little mistake. And all a cardinality is just a property that describes the number of elements in something, right? So if we look at this, the way it is now, we're saying a student has a phone number. Maybe we could say a student can have several phone numbers. Maybe a phone number could belong to multiple students, right? Maybe an address could belong to multiple students if they live together. You could have students with the same name, right? So cardinalities can kind of show the number of things in this relationship. So let's look at this example here. The model now becomes this. So it's a little more complex. Our model is a little more complex. So a student now has a date of birth, a forename, which is first name, surname, which is your last name, a street address, a house number, a town, a postcode, and 3 phone numbers, right? So maybe our cardinality is up to 3. A student can have up to 3 different phone numbers. So our model has been expanded a little bit. So how do we know when we want to use modeling? Well, if a solution has interactable parts, so if one part of the solution can interact with another part of it, you should make a model as soon as possible. What you can then do is take that model data and pick what data the user sees and manipulates, and what the user does not see or manipulate. So let's think about like Amazon, right? If we were to model out Amazon's website, there's a lot of data that we as Amazon users, when we just go buy things, there's a lot of data that we don't see, right? So there has been data that has been chosen for us to see. So the price of the thing, the little picture, description, reviews, whatever we can see on Amazon's end. But there's a lot of data that we don't see. And that's something called a user view. And then you can model the navigation. So the user should not navigate through excessive views to get what they want. And then prototype the interface. So this doesn't need to be complex. A paper prototype usually works. So, let's just think about modeling. Let's use Amazon again for an example. Let's model an Amazon interaction, right? A user goes to buy something. The user should not have to navigate through 500 different views to get to what they want. Maybe they start on the home page, they type in what they want, they click on it, they add it to their cart, they go to their cart, and they buy it, right? You could keep those views very simple. And then you want to prototype kind of what that would look like. So if we were to write the software of what those web pages would look like, we don't have to do anything crazy. We could literally draw it on paper and just have a very basic layout or a model, right? We could have a very basic model of the web page just for an idea. So some things to remember about modeling. The primary concern of modeling is we want to portray information, right? And we want to make sure that our model is actually useful. So if our model is useful and it is portraying some kind of information, right, given the context that we want and whatever information we want shown, then it's worth it to have a model. We have a concept of formality. So we have formal and informal models. Formal models have some kind of rules and limitations in place, but they are important for a smooth exchange of information. So we're going to be using a specific type of model called a UML in this class. UML has some rules in place that say, this is kind of how a UML looks. These are the way that the relationships between our entities look, that kind of thing, which can be kind of limiting in a way. But it is important because if we know what those rules mean, it's very smooth to take that model and turn it into some kind of software. Informal models are earlier things in your process where you're just thinking about ideas and spitballing with coworkers or yourself. If you're just trying to get ideas down and you're doodling out some kind of really basic model that doesn't really follow rules or anything, that would be an example of an informal model. Some more things to remember. Accuracy. It's important to know that all models are kind of wrong. No model is 100% accurate just by nature of them being an abstraction, right? Models always abstract some kind of information, even if they're very detailed. But they can be very useful. For example, a modern map, if we were to go buy an atlas or something, a map is not 100% accurate to the terrain and landscape, but it works for navigation, right? It is useful. So when you're making your model, kind of ask yourself, what level of accuracy do I need here? Precision. All values are continuous or infinite. So, you could be infinitely specific or infinitely vague with your model. Just constrain your information to a restrictive box, give some kind of max and min to a certain decimal point. This is dealing more with specific values here. So let's say that you're having let's go back to the student model, right? If we were to model a student has a GPA, you would want to give that GPA some kind of marker, right? That says, this is a number. I really only want up to maybe 2 or 3 decimal places. It doesn't need to go further than that. All right, so now I'm going to switch over to a actual modeling software, kind of show an example of the UML model that I talked about earlier, and after that, that will be all for the video. All right, so I'm now in my modeling software. On the syllabus for the course, it says that we may use something called Lucidchart as our modeling software. I'm trying this one out called diagrams.net, which is free and you don't have to have an account or anything. So we may switch over to this depending on how robust it is. I haven't really messed with it too much yet. So I'm going to show you an example of the model that we are kind of most focused on with programming specifically, which, like I mentioned earlier, was called UML. We'll talk about UML a little bit more once we get into data types and stuff like that. So this UML will not be 100%, programming accurate. If you've seen UML before, there may be some things that you notice are not exactly correct. I'm just going to show kind of a very abstract UML. So let's say that we want to model some kind of ordering system, right? A customer is going to order something, and maybe we have 2 different kinds of orders, right? Maybe we have a special order and just a normal order. So how do we go about doing that? Well, the first thing we want to do is identify the entities that we are actually going to be modeling, right? So I know that I want to model a customer. I know that I want to model an order, and I said I had 2 types of orders. I had a special and a normal order. So I'm gonna kind of consider all of those things entities, and we'll go ahead and start with the customer. So on diagrams.net, and I may do some more videos or something on diagrams.net if I decide to go through with it, but down here at the very bottom, you'll see that we have a category of diagram called UML, and like I mentioned earlier, that's kind of what we're going to be using for modeling our code solutions. So we'll talk about classes, fields, and methods later, but for now let's just consider this an entity, right? And I'm going to call this customer. So this is my customer entity. We mentioned earlier that entities have attributes, right? And attributes are what we call fields in programming. So a field is just an attribute about the thing, right? The thing here being customer. So let's think about what we want to show about a customer. And for now, all I'm really concerned with is the customer's name. And I would like to know the customer's location. And we could break this down to be a lot more specific, right? We could have a first name, a last name, a street address, a city, a state, a zip code, all that stuff. I'm just going to keep this pretty simple. Now, when we're modeling, we could just leave it at that, right? Name and location. But if I wanted to take this and turn this into some kind of code, right? I would want to know what is a name, right? Is name a number? Is it a decimal number? Is it a Boolean? Is it a true-false value? Is Boolean? What is it? So what I'm going to do is I'm just going to say name is some kind of text here, right? I don't want name to be a number. I want name to be some kind of text. And we represent that with a colon. So we have what the thing is, then we have a colon, and then we have, what the type is. So in this case, name, I just want to be some kind of text. Same thing with location. Location is going to be some kind of text value. Okay? Now, as far as methods go, for now we can just think of methods as actions, right? So we know that customer has 2 fields or attributes, the customer's name and the customer's location. What actions do we want this customer to be able to take in our system, right? So like I said, this was like an ordering system. Maybe all I want the customer to be able to do is send an order, and maybe I want the customer to be able to receive an order as well. right? So they can send their order to the system, and then they can receive their package or whatever. Confirmation, however you want to think about it. So that's customer, right? I've modeled a customer. Obviously, it's very abstract, right? Because you could get infinitely detailed with your customer. You could have their credit card number. You could have their, anything about a customer you want. This is all I'm interested in for this model. So let's tackle order. Now, what things do I want to keep track of about an order? Maybe I just want to know the date that the order was made. And what type of data is a date? We can just literally say that it's a date, right? You made the order on August 29th, 2021. That's a date that would work for this data type. And maybe I also want like an order number, right? And I'll say an order number can be some kind of text value because sometimes confirmation numbers have letters in them. So we'll just say that's some kind of text value. Now, let's say that we want to tackle these actions, right? So what actions can happen with an order? Well, maybe the order can be confirmed. And maybe once the order, maybe someone cancels the order or whatever, so we could say the order can be closed, right? So now let's think about the relationships here, right? Because we said models have entities and they have relationships between them. So what is the relationship here? And it really could go however you want to do it as the person creating the model. So kind of how my brain works is I'm going to say that the order is related to a customer. You could say that a customer places the order, but I'm going to relate it this way. And here's an example of what I meant about formal models having rules, right? So let's think about the rules here. These boxes, the top box is the name of the entity, the middle box are the entity's attributes, and the bottom box are the actions that the entity can take. That's a rule, right? I couldn't put my attributes in the bottom box and my actions in the top box, for example, right? UML has a very specific layout of how you do your entities. Another example here is another example actually is the colon, right? So we have the name of the attribute, we have a colon, and what type of data the attribute is. That's another kind of rule that UML has. Another example of a rule is the line here, right? So the direction that the arrow is pointing kind of shows the relationship here, right? So the relationship is going from order to customer. And believe it or not, the arrowhead actually does matter, right? You'll see I have an empty arrowhead, it's white. I actually want to change that arrowhead, and I'll tell you why here in just a second. So I'm going to make this a black arrowhead. And what I'm also going to do is I'm going to add in that cardinality, right? And we said that with cardinality, if I can figure out how to do text here, let me see. Let me just insert some text. Cardinality just says how many things are associated in this relationship, right? So on the customer side, an order can be placed by, we'll say, one customer, right? Multiple customers can't place one order. That doesn't make much sense. So an order is placed by one customer. That might be my cardinality in this relationship. Now let's say that I want to do the cardinality on the order side, right? I'm going to put the letter N here, which also can kind of mean multiple, right? So we'll say that an order can be placed by one customer, but a customer can place N number of orders, right? A customer can place multiple orders. And that kind of makes sense. Now, this is a little advanced of a topic for this course, but I am going to talk about it. I did say that we had two different kinds of orders, right? We had a special order and a normal order. What I'm actually going to do is I'm going to copy the order table here, or the order entity. I'm going to call this one special order. And I'm going to call this one normal order. So, in programming, we have the concept of parent and child relationships. And we could say that order is a parent to special order and normal order. And what that means is both special and normal order contain everything that a regular order has, right? So the date, the order number, the confirm and close actions. But they may have something special about them in addition to this stuff, right? So a special order might have an additional action. Maybe we could say, maybe there's some kind of dispatch that happens here with a special order, right? And again, I'm just making this up. A special order has its own action called dispatch. And maybe normal order has its own action called, we'll just say receive, right? These don't have to make sense, my actions, right? But we can see that these are different, right? But confirm, close, date, and number all come from my parent here, right? Which is just the regular order. So how we model that relationship, and again, you'll go into this a lot more in CSCI 1260. This is a concept called inheritance, if you are curious. We'll say that special order and normal order are both related to order, but my black arrowhead kind of has an action-based relationship, right? An order is placed by a customer. That's kind of what this black arrowhead represents. It's an action. So special order and normal order aren't really actions that are being taken on a regular order. It's more of a relationship, right? Special order is a subset of a regular order. Normal order is a different subset of regular order. So another one of UML's rules is, depending on what the relationship is, you will have different arrowheads here, right? So instead of a solid black arrowhead, in this kind of relationship, we have a empty white arrowhead. And I don't expect anyone to remember this, but this is a concept called generalization. So we have my parent and my children, or if we want to think about it in terms of programming, we have my superclass and my subclasses. And we don't go into that too much in 1250, but I just wanted to show you this is how you can model something like that. Okay, so here's a very, very basic example of a model. You'll notice that we don't put cardinalities here because of the type of relationship that we have, right? A special order can't be multiple orders, right? You couldn't have that numeric value between these because it's describing specializations of an order. So that does it for this video. We'll discuss modeling some more in lab this week, and we'll do some examples. I think I do like diagrams.net. I want to play around with it a little bit more, but there's a good chance that we'll use it instead of Lucidchart. So if you haven't made a Lucidchart account yet, I wouldn't worry about it until lab, because I think we're going to use this. It's a little bit better.